Now, integration is also referred as antiderivative. Now, why do we call it as an antiderivative? First, we're going to take a couple of examples on antiderivative properties, and then we're going to go into the depth of the integration techniques. So why is it called integration? Now, integration is actually derivative we already did. So let's say if I do the derivative of, let's say, any function, for example, let's say x cubed plus 4x plus 3 to the power 8. So the derivative of this is nothing but 8x cubed plus 4x plus 3 to the power 7 times 3x squared plus 4. Now, when they say that, this procedure from here to here is called differentiation, and procedure from, if I have got this function, if I some way I can get the original function back, we call it as anti-differentiation. So this is differentiation, and this is anti-differentiation. So the general notations that we use for anti-differentiation is actually this this notation. So whichever function you're integrating. Now, let's say if I wanted to integrate 8 times x cubed plus 4x plus 3 to the power 7 times 3x squared plus 4, and I'm just going to attach with whichever variable you're differentiating, integrating with respect to. So the function which you're integrating actually here is this, and it is read as, how do we read this? So they'll say integrate this function with respect to x. And now this property of differentiation from here to here and anti-differentiation from here to here helps us to get the answer for this expression. So when you integrate both the sides, actually, the differentiation and integration actually cancel, and eventually your answer is x cubed plus 4x plus 3 to the power 8. So this is the answer. And now you got to understand that if there was, let's say, a constant here, its derivative still would have been the same. So because the derivative constant is 0. So what happens is that when you integrate, you got to put the answer with a constant, because you really don't know whether the original function had an integration, had a constant or not. So this is a simple explanation for anti-differentiation. So now let's take the another example, which is first part is to differentiate, which is ln x squared plus 4x plus 3. So first step is pretty simple. Now when you differentiate, actually it is the chain rule. So the chain rule differentiation here, it is ln fx derivative is 1 over fx times f dash x. So ln x squared plus 4x plus 3 derivative is going to be 1 over x squared plus 4x plus 3 times 2x plus 4. So this is the differentiation process. Now then they say, okay, hence you integrate this answer. So hence you integrate this. Find the expression for integration of this. Now antiderivative for this. So when you look at the antiderivative, now you can see that it's exact same thing what you derived. So if I integrate this expression, I should get this as my answer, ln x squared plus 4x plus 3. So this answer is straight away ln x squared plus 4x plus 3, but don't forget to add a constant. So see, this is the exact property of antiderivative. So let's take one more example on this. So the question here is that differentiate, let's say, e to the power x cubed. Now when I take e to the power x cubed, okay, the derivative of e to the power x cubed is, so e to the power x cubed derivative is 3x squared times, so first you're going to do e to the power x cubed is e to the power x cubed itself times derivative of x cubed, which is 3x squared. So next up is hence evaluate. Now the moment they say hence, there is some link between this and this. So what you do is, now if I have to, basically if you see here, if I have to do integration of 3x squared e to the power x cubed, it's exact opposite of this, right? So if you just integrate both the sides here, so this get canceled, and so your answer is actually e to the power x cubed plus c. So this is the third example. Let's take one more example where you got to do a little bit of adjustment. So here we go. So here the question is that the function is y equals to ln x over x. So hence find out the integration of this. The first part is that to do the derivative and hence use that to find this. So let's do the derivative. So dy by dx is x squared x times the quotient rule here I'm applying. So vu dash minus uv dash over v squared. So that's what I'm exactly doing here. So x squared x times ln x. Now ln x derivative is 1 over x minus ln x times 1. So this and this get cancelled. So what you get is 1 minus ln x over x squared. And the interesting part here you see is that, okay, it is the exact same thing that I'm trying to find out the integration for. So the answer is straight away ln x plus ln x over x. So since this is the exact derivative of the function ln x over x, hence the integration of this function is just ln x over x. This is ln x over x plus c. Now the one with a little bit of adjustments is here. Let's say I wanted to find a 2 times 1 minus ln x. So sometimes they say that, okay, this is here, it is given to you, but they'll say, okay, find the derivative of this and hence integrate 2 minus 2 ln x or x squared. So this is suppose given to us. So now we just proved that the dy by dx is, so the derivative of, I would rather write like this. So derivative of ln x over x is actually 1 minus ln x over x squared. Now, if you notice that I needed 2 here, so if I multiply both the sides by 2, it's being constant, doesn't affect left-hand side. So when you integrate this actually, so integration of 2, 1 minus ln x over x squared is actually nothing but 2 times ln x over x plus c. So this is in short the antiderivative property of the function. And now let's take the proper integration properties.